Hello everyone. In this video, I will demonstrate the design of a synchronous buck converter and simulate it using QSpice. First, I will show the operation and the design principles for sizing the inductor and the capacitor. And finally, we'll look closer into this practical design example, as you see here on the screen. A buck converter reduces the input voltage. For accomplishing this, you can think of it as two switches, which alternate between the input voltage and ground. Now, only an LC filter is used to get a smooth output voltage and current. There are two states of the buck converter. In the first stage, Q1 is closed and Q2 is open. That's the state here. And the circuit reduces to this one shown here on the right side, where we have the input voltage, which is connected with the inductor and the output capacitor and output resistor. In state 2, Q2 is closed and Q1 is open. This is this state here. And the circuit reduces to the circuit shown here on the right side, where the ground is connected to the inductor, and then the inductor is connected to the output capacitor and the output resistor. Now we have to analyze the two states. Let's start with analyzing the inductor. In state 1, the inductor voltage can be calculated with following this loop. And then it results into the input voltage minus the output voltage. So I can draw a line here for the inductor voltage. This line means the input voltage minus the output voltage, which is positive. In state 2, we have the loop here. So the inductor is only connected to the output. This means it's negative, and the inductor voltage is minus the output voltage. So this one here is minus V out. And then again, after one duty cycle, we are in state 1. Now let's have a look at the inductor current. The inductor current can be described by this formula. It's IL equals 1 over L times the integral of the voltage VL dt. Then for state 1, we have a positive voltage on the inductor. This means we have a rising current. And in the state 2, we have a negative voltage, which means we have a falling current. And this is our current ripple, which is used for the design of a buck converter. To calculate the current ripple, we can use this formula. And now, for example, I will calculate it for the state 1. It results the same if you use it for state 2. So delta IL equals 1 over L. So we have an integral from 0 to dt. And then we have the voltage, which is input voltage minus output voltage, our inductor voltage for state 1. And then only has to be calculated. AL. It's a very easy integral. It's just times dt. This equation can be now used to size our inductor. For the current ripple, generally a value between 10% up to 30% of the DC output current is used. Now we have to analyze the voltage and currents at the capacitor. For the current, we simplify that the output current we see as stable DC, and the ripple current, which we before showed for the inductor, is the current going into the capacitor. So IC is basically the ripple current from before, just around 0, and this is our current ripple for the capacitor. Now we have to analyze the voltage at the capacitor. The voltage is described by this formula, Vc equals 1 over C, and the integral of the current at into the capacitor. Now if you look at the current, we can get the voltage which we have. So when the current is negative, the voltage falls, something like this. And once it's positive, it rises until it's negative again. So we have a shape roughly like that. And that is our voltage ripple for the output or the capacitor. Now we as well want to get a formula to size our capacitor. Like before, we could calculate the integral for one sector from 0 to dt, for example. Or we simplify it and just calculate the triangle area here, because this gives us the whole voltage ripple. So we apply this formula and just calculate the triangle. And this now can be used to size our capacitor.
One design principle is the volt-second balance. It states that in a steady-state condition, the voltage over one period is 0, meaning that the inductor current over one period is neither rising nor falling. From here to here it's the same value. Now this formula can be used to calculate the output voltage resulting from a buck converter. So we have in state 1, we have in minus V out times dt, and then we have state 2, which is minus V out minus dt, and this equals 0. And now I will quickly calculate this equation. And then we have the result, which shows the required duty cycle for a output voltage and the given input voltage. Now let's come to our design example. Here are the equations we just derived, and that's the requirements for this buck converter. I chose input voltage of 48 volt, an output voltage of 12 volt, an output power of 120 watts, and I want the output voltage to be below plus minus 0.5% of the output voltage. Now let's start with our design. First off, we calculate the duty cycle, which is just, if you plug in the numbers, 0.25. Then as a switching frequency, I chose 100 kilohertz, which gives us a period time, which is 1 hour with a switching frequency of 10 microseconds. Then I want to size our inductor. As stated before, generally it's chosen between 10 to 30% of our inductor current. The output current, which is our inductor current, is calculated by P out over V out, which gives us 120 watts over 12 volts, so 10 amps. So our current ripple should be around 20%, 10 amps. Current should be around 2 amps, which we use for the calculation. Now to calculate the inductor, I use this formula, solve it for L, and plug in the numbers, which gives us a value of 45 microhenry. To calculate the capacitor, I use this formula, which we derived before, and the requirement of 0.5% output ripple. The 0.5% output ripple is 60 millivolt. And now this formula is solved for C. All the values are already known, so the numbers can just be plugged in. And we get a result of 41.7 microfarad.
For the 45 microhenry calculated inductor, I chose one with the same inductance and a series resistance of 18.3 milliohms. For the capacitance, which should be minimum 41.7 microfarads according to my calculation, I chose one with a quite a bit higher value of 82 microfarads and a series resistance or ESR of 25 milliohms. Later we'll see why this higher value will be required. Now we will simulate the buck converter for the PWM. The C block and an incorporated advanced PWM is used, which I showed exactly in a previous video. I will put a link into the description. Additionally, I used a discrete gate driver, which I as well illustrated in my last video. I will put a link into the description. Now for the buck converter, it's actually just those components. First, I will show the simulation with using no parasitics. So I will use the inductance with no series resistance and the capacitance with no ESR. And later I will show the same simulation with the parasitics. And then we'll see why I had to choose a way higher capacitance to reach our design goal. Now let's start the simulation. Okay, around here we have a steady state. We can zoom in and take a closer look at the results. First, let's look at the current ripple. Looking at this, we would want to have a current ripple of 2 amps, the 20% of the 10 amps steady state output. And we see that we're coming quite close from 8 to 9.9, so it's very close to the 2 amps output ripple. Looking at the output voltage ripple, it was designed to be output voltage ripple of maximum 60 millivolts. And if you look here, we are here from 10.74 to 10.7 or 10.8 almost. So we are very close to the 60 millivolts. Now I added the values for the series resistance on the inductor, and I used the chosen capacitor of 82 microhenry with the ESR of 25 milliohm. Now we run the simulation again. And now if we zoom in, we'll see that from the results, if you look at the output voltage ripple, that we have a voltage ripple of around 50 milliohms. And like this, the requirement is met, but as well just met, even though I chose a way higher capacitance. The output voltage of the 12 volts is not reached or not stable, and therefore we would need a feedback which feeds back into the controller, and the duty cycle is regulated. In addition, we would not like to have an overshoot which is too high above the 12 volts. Let's see if a solution for this comes up in a following video.